In this video, we discuss derivatives of a Laplace transform. We've already discussed how to take the Laplace transform of a derivative. Now we're kind of doing that in reverse. We are going to derive this result in the case when f of s, the Laplace transform of f of t exists, and it's possible to interchange the order of differentiation and integration. It's not always possible to do this. So there is some fine print here. But we're not going to talk about the fine print in this class. We're just going to assume that it's possible to do this, and then we're going to see what the result is when it is possible to do this. So, and then we're going to apply it in a couple of examples. So let's say that f of s exists, and it's possible to interchange that order of differentiation and integration. Well, then in that case, the derivative of f with respect to s, which can be denoted that way in Leibniz notation or this way in prime notation, is the derivative with respect to s of the Laplace transform f of s, which is defined this way. It's the integral from 0 to infinity of e to the negative st times f of t dt. Now, if it's possible to interchange the order of differentiation and integration, we can pull that derivative operator inside. Now, since this is a function of two variables, I should change this derivative with respect to s to a partial derivative with respect to s. Well, in that case, we've got a function of t, which we're treating as a constant whenever we're taking a partial derivative with respect to s, times e to the negative s times t. Well, then I would bring the constant down if I'm taking that derivative, and then I take the derivative of e to some power. It's going to be e to that power times the derivative of the inside with respect to s, treating t as a constant. So that's going to give us a negative t here. Now that is the definition of the Laplace transform of this function. Remember, the Laplace transform is the integral from 0 to infinity of e to the negative st times the function itself. So that's the Laplace transform of negative t times f of t. But most of the time when we use this theorem, we actually use it in reverse. We don't take the derivative of the transform and show it's equal to this. We say that, notice that the Laplace transform of this is equal to that. So if you have t times f of t, and you want to compute the transform, one way that you could do it is find the Laplace transform of f, and then take its derivative with respect to s. And then if you've got this -1 here, you get exactly this. And if you don't have the -1 here, you can multiply both sides by -1 and you would get that. Now let's see what would happen if we take the derivative again. I guess I should have said if we took the derivative again. So that's going to be the derivative with respect to s of the first derivative of this with respect to s. So the first derivative of that with respect to s was this expression. So we're taking the derivative with respect to s of the integral from 0 to infinity of negative t times f of t times e to the negative st. And the circumstances are the same. So we're assuming that we can interchange the order of differentiation and anti-differentiation, or differentiation and integration. So we can pull that derivative operator inside, but this is a function of t and s, so we would change that derivative operator to a partial derivative operator. Well, in that case, this negative t times f of t is a constant, and we're differentiating this guy again with respect to s. Well, the derivative of e to some power, if that power involves the variable that we're differentiating with respect to, is e to that power times the derivative of the inside with respect to s, treating t as a constant. So remember, that's how we take partial derivatives. Well, that just ends up resulting in multiplication by another negative t. So every time we do this, every time we take a derivative over here, we're going to end up multiplying by another negative t inside. Let's see. So now if I simplify this, this is the integral from 0 to infinity of negative t times negative t, which is positive t squared times f of t times e to the negative st. We're taking an antiderivative with respect to t and then evaluating the improper integral. Well, that is by definition the Laplace transform of t squared times f of t. Now, since every time we take the derivative with respect to s, again over here, we end up multiplying by another negative t inside. What that tells us is that in general, the Laplace transform of negative t to the nth power times f of t is equal to the nth derivative of f of s. Or in other words, it's the derivative with respect, or the nth derivative with respect to s of the Laplace transform of little f of t. So I compute this. It's going to be a function of s. I take the derivative n times, and that's going to give me this. Now, most of the time, this theorem is not written this way because we like to think of this a little bit differently. We usually like the negative to be on this side, so that if you have the Laplace transform of some power of t times f of t, you would just get the result over here. Well, in that case, you'll have this. That nth power applies to the -1 and the t. And if I want to get the t to the n times f of t by itself, this is an equation. I can just multiply or divide both sides by this -1 to the n, which is the same as multiplying both sides by -1 to the n. And so we end up with this version. Now this will allow us to take the Laplace transform of some power of t times f of t, where f of t is a function that we know the Laplace transform of, some function in our table. But in practice, we usually don't use it for that. We usually use this when we are solving initial value problems in which the differential equation does not have constant coefficients. So maybe you've got a polynomial in front of your y double prime. That's when we would use this. So let's apply this to a function of t, and then let's apply it when we have a derivative here, which is the more common usage of this theorem. So let's say you have t times e to the 3t times cosine of 2t. Now we could use our first translation theorem. You can think of this as e to the at times t times cosine of 2t. That's one way of doing this. Now you can also use this derivatives of a Laplace transform theorem. So let's practice with both of those. Remember, our first translation theorem says this. If you have e to the at times f of t, the Laplace transform of that turns out to be the Laplace transform of f of t, that's f of s, with the s replaced by s minus a. That's going to give us f of s minus a. So let's compute that way, and then we'll use this new theorem to evaluate this. On this case, my e to the at is right here, f of t is everything else. So through pattern matching, we see that a is equal to 3. And according to this is equal to the Laplace transform of t times cosine of 2t. And then we replace the s with s minus a, and a is 3, so we're going to replace the s with s minus 3. So I'll go to my table of Laplace transforms and look for this one. And it's actually right here on this page. It's number 23. Got t times cosine of 2t right there. The Laplace transform of t times cosine of 2t turns out to be s squared minus k squared over s squared plus k squared quantity squared. So k is equal to 2 in our case, and I think I'll write that transform down just from the table. Okay. And that tells me that if k is equal to 2, we're going to have s squared minus 2 squared, which is 4, over s squared plus 2 squared, which is 4, quantity squared. And then we're going to replace all the s's with s minus 3's. So this will be s minus 3 squared minus 4 over s minus 3 squared plus 4, quantity squared. And that's the Laplace transform of this guy. Now that's using the first translation theorem. Let's show that we get the same result using the other theorem. So now rather than looking at this as e to the at times f of t, I want to think of this as t to the first times f of t. So this is t to the n times f of t. According to our derivatives of the Laplace transform theorem, the Laplace transform of t to the n times f of t is negative 1 to the n times the nth derivative of the Laplace transform of f of t with respect to s. So in this case, n is equal to 1. So we're going to have negative 1 times the first derivative with respect to s of the Laplace transform of f of t. And we could actually use our first translation theorem to compute this Laplace transform. Using the first translation theorem, we see that a is equal to 3. So we're going to get the Laplace transform. I'm ignoring this derivative with respect to s right now. I'm just focusing on what's inside the brackets. We'll get the Laplace transform of cosine of 2t. And then we're going to replace all of the s's with s minus 3's. Well, according to our table, the Laplace transform of cosine of 2t is s over s squared plus k squared, where k is 2, so we're going to have 4. So I've got negative 1 times the derivative with respect to s of this. And in our numerator, we're going to have s, and the denominator will have s squared plus 4. But then we replace s with s minus 3. And then we're going to take the derivative of that with respect to s. So the derivative with respect to s of s minus 3 over s minus 3 squared plus 4. Now that requires us to use the quotient rule. So of negative 1 times, from calculus 1, low d high, that's the bottom function, times the derivative of the top function with respect to s, which is just 1, minus high, which is s minus 3, times the derivative of the bottom function with respect to s. This requires us to use the chain rule, so we'll have 2 times that s minus 3 raised to the first times the derivative of the inside, which is 1, plus the derivative of 4, which is 0. So that's low d high minus high d low, or the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, all over the bottom function squared. And so we have negative 1 times s minus 3 squared plus 4 minus this, that's minus 2 times s minus 3 squared, all over s minus 3 quantity squared plus 4. Quantity squared again. So I've got one of these here and then another one of those here. So that means I've got negative 1 of those. So I've got 4 minus s minus 3 squared. And all of that's being multiplied by that negative 1 outside. So if I wanted, I could distribute that negative to the numerator here, and that would just flip the order. I'd have negative 4 plus this, which is the same as the positive version of this minus 4. Okay, so that was a lot, but we ended up here. I just want you to note that what our answer was using that derivatives of a Laplace transform theorem. It's the same answer we got up here. Notice how much less paper I had to use for this first theorem. So in this case, it would have been much easier to just go straight for this theorem, especially given that t times cosine of 2t was already in our table given by this. Okay, so in practice, we don't actually use this in this way. Typically, we use this in this other way. So let's say you're solving a differential equation and your differential equation has variable coefficients. Let's say that the Laplace transform of y of t is equal to big Y of s, and you want to compute the Laplace transform of t times y double prime. Well, according to our theorem, this is t to the n times f of t, n is equal to 1. So according to the theorem, this is going to be -1 to the nth, which is 1, times the first derivative with respect to s of the Laplace transform of f of t. So that's the Laplace transform of y double prime. This is actually the context when we would typically use this theorem. The Laplace transform of y double prime is s squared times y of s minus s times little y at 0 minus y prime at 0. Now, I don't have my initial conditions, but I know that y of 0 and y prime of 0 will be given constants. When I take the derivative of this is a function of s times a function of s, so I'll have to use the product rule. So we'll have -1 times derivative of the first times the second plus derivative of the second times the first. And then we've got a constant times s, or constant times -s. The derivative of a constant times -s is at -1 times the constant. And the derivative of the constant with respect to s is 0. And all of this is multiplied by that -1 over there. So I would distribute that negative. So I'd have -2s times y of s. I think I'll bring that s squared out front, minus s squared times y prime of s, minus a -y of 0. So that's adding y of 0. Now, this changes things. Before, when we were using the Laplace transformation to solve a differential equation subject to some initial conditions evaluated at, or prescribed, excuse me, at t equals 0, the corresponding equation that involved y of s was just an algebraic equation. So we just did some algebra to get y of s by itself, and then we took the inverse transform. That's what happens when your differential equation has constant coefficients. Now, if the equation does not have constant coefficients, but it has variable coefficients, we can also use the Laplace transform to solve it. But that will involve doing something like this. And that means you end up with a derivative of the transform in the equation that results from taking the Laplace transform of the original differential equation. So what it's going to do is it's going to take your differential equation in t, and it's going to transform it to a differential equation in s. So we'd have to solve for y of s in that problem where you have a y prime of s in your differential equation. So most of the time what we're going to see in our class is we're going to see that when we've got a variable coefficient here, or in our differential equation, if our differential equation has variable coefficients, we're going to end up with differential equations in y of s instead, and most of those are going to be first order differential equations. So we'll have a first order differential equation that we can solve, usually using an integrating factor. So that's when we would use this derivatives of Laplace transform fact. This will come up right here. We will come back to that a little bit later after we learn about the convolution. Let's stop here for right now, and we will learn about the convolution, and then we'll talk about solving integral equations and integral differential equations.